Welcome, everybody. Welcome to this first Movella Sports Conference. The Sports Conference is about combining sports and kinematics. And today, our aim is to give you valuable insight into different tools that can be used and combined for performing analysis in research and in sporting environments. This also includes a detailed look at the latest innovations for measuring human motion in sports, such as EMG, force plates, but also software applications that can calculate kinematics. During this sports conference, our speakers will share their insights about the technology and the application in motion capture. We hope that by showing the innovative combination of analysis tools for researchers and sports scientists, that they will learn new ways to investigate an athlete's performance capabilities. Next up is our speaker, Jonathan Haggard from Delsys. He will tell you something about EMG as a tool for performance and rehabilitation. And yeah, I hope you guys are going to enjoy it. I want to give the word now to Jonathan. So Jonathan, you can start sharing your screen and unmute yourself, and then you can start the presentation.
Hello, Jordi.
Hello, everybody. Here I am again. So I hope you enjoyed the presentation of Marcus on the introduction of Movella. I hope it's a little bit more clear now. And otherwise, like I said, feel free to post any questions in the chat. Next up is our speaker, Jonathan Haggard from Delsys. He will tell you something about EMG as a tool for performance and rehabilitation. And yeah, I hope you guys are going to enjoy it. I want to give the word now to Jonathan. So Jonathan, you can start sharing your screen and unmute yourself, and then you can start the presentation.
Hello, Jordi. Hello.
Yes. Hello. You can.
Hello,
go.
Jordi. Can you hear me?
Yes.
Okay. Yeah, no, I'll go. To get started. Yeah, so thank you very much for the warm welcome. So my name is Jonathan from Delsys. I'm working out the European office based in Manchester in the United Kingdom. Today we'll be presenting, as Jordi described, EMG as a tool for performance and rehabilitation within sport and in terms of the human movement sciences research field. So to start, the main sort of real objective of the talk today is to understand really the application of EMG and kinematics as a tool for more of a unification of different biomechanical metrics to be able to give us a real deeper understanding into how multiple different tools can give us a much deeper insight into the way in which the brain controls movement, but then how the muscles control the limbs and the way in which we provide stability and force through production and movement as well. So with the agenda, a brief sort of introduction will be to Delsys as a company, the sort of support we provide to the human movement sciences community, but then also the sort of research arm that we do have, as well as the charitable work. Moving on to sort of the concept of really what is EMG, the applications of this within the human movement sciences field for sports rehabilitation and performance, and then applying this alongside kinematics to be able to give us that sort of more rich insight into the human movement and control of movement. Then a brief video we'll go touch on about the sort of systems integration between Delsys and Xsense through our sort of streamlined API integration into the MVN software. Then sort of touching on a few user cases to really try and give an applied feel about how sort of customers are currently using these technologies to be able to inform their practices, whether that's from performance or a rehabilitation standpoint. And then finally, trying to finish up, hopefully with enough time to answer any questions that do come in during the talk. So please, if you do have any questions, feel free to put these in the chat, and we'll be sort of happy to answer any of these at the end of the talk there as well. So to start, sort of who are Delsys? So we are a world leader in the design, manufacture, and marketing of a portfolio of sort of high performance electromyography instruments. We're founded back in 1993 by Professor Carlo De Luca, and to this day, we still really remain driven by collective passion to create high quality and high fidelity electromyography equipment. And through sort of rigorous research and commitment for development, we have created a wide spanning array of high fidelity wireless technologies that we're known for today and that are used in a really sort of wide span of applications across the human movement sciences field. So obviously I'm presenting today from the European office, but we have multiple offices located worldwide. Our head office is over in Boston in the United States, where a lot of the sort of research and development does happen along with sort of the main operational days. But in 2017, we opened the European office to really provide a central hub for our European customers to provide sales support, technical insight, but also educational support as well and outreach to support locally our customers and provide context and applications for how our technologies are used within the applications. But we also have our sort of satellite offices also in China and Japan, and a sort of network of worldwide distributors and partners. So no matter really where you are tuning in from today or where you're based currently, there'll be a sort of Delsys representative in your area who'll be able to support any questions and provide sort of technical and application support for there as well. But Delsys is really far more than just a commercial entity through the world of industry. So our research arm, Altec, are continuously pushing the limits of research within the field of human movement sciences. Through constant innovation, new state-of-the-art technologies and signal processing tools and sort of new concepts about how we use technology are being developed to help researchers answer some of the key questions that still remain within our field. And Professor De Lucas really instilled the message of us to give back to the community, and his legacy lives on through the De Luca Foundation. So through equipment donations and financial support, we're able to give back to the community that supports us from a commercial point of view. And that is supported through sort of funding research, through student mentorship, through philanthropic support to provide sort of mindful pathways to emerging researchers and equitable access for opportunities within science. And we still really do share the same real mission as a lot of researchers within the community. And at Delsys, we join really at the starting point for most of these sort of scientific questions, where a lot of the work we do requires conceptualization of new products, new theories, new concepts, and this leads us to the development of that sort of product base through the engineering principles. And with the research arm, we then support the ongoing desire to advance our understanding of the human movement together with the scientific community, and then applying that into the real world through the application side, and our sort of application engineers and support engineers who then help guide researchers to the sort of best practices and best implementation of our technology within their research questions. But the sort of real main question and why we look at EMG is how does the brain control movement and control the muscles? And important questions really do still remain about how muscles are controlling these sort of motor network and neural network. And questions include sort of what are the basic motor control and muscle control properties that govern muscle contractions? Does fatigue affect specific muscles differently? What sort of factors may influence muscles performance? And by understanding some of these questions, we can really help to, I guess, elevate the sort of scientific practices that allow us to better understand and treat motor disorders, enable therapists sort of improvement in the way in which they go about rehabilitation and sort of increase the effectiveness of some of these rehabilitation protocols, but also able sort of more sports performance and trainers to develop more effective training protocols to elicit higher motor adaptations and then higher sort of sports performance. But then also on the engineering side, improving sort of prostheses control, rehabilitation from that side, and sort of neural interfaces to be able to take the next step beyond and move into sort of the next possibilities of where the research is going. So again, it brings us back to sort of the product itself and what is, I guess, EMG. So to break that down very sort of simply, we can look at the sort of electromyography. Electro is the electric, myo meaning the muscle, and then graphy is the graph and the plotting of this sort of electrical signal that comes from the muscle. And sort of to quote Professor DeLuca, EMG or electromyography is the sort of study of the muscle function through the inquiry of the electrical signal that the muscle emanates. And this is sort of simply put, so it's an easy sort of conceptualization of the idea in which EMG, so as the sort of muscle contracts, there is the electrical signal which emanates from the muscle, and then we are able to capture this through the sort of high fidelity technology that we do offer. So to briefly really sort of revisit the foundations and the origins of the EMG signal and how the brain controls movement. So the brain sort of is the main starting point for all of this sort of electrical signals. And as the brain sends electrical signals down the spinal cord along motor neurons, these originate from the ventral horn of the spinal cord. And each motor neuron innervates a very specific group of muscle fibers. Collectively joined together, we call this a motor unit. And a motor unit is really the single smallest controllable muscular unit that we can measure and offers a real sort of sneak behind the curtain into the intricacies of the neuromuscular system and sort of motor control, rather than just that sort of global representation that we do see from the EMG signal. And muscles are composed of sort of many hundreds and thousands or hundreds or thousands of motor units that contribute towards movement. And each motor unit contracts when it receives a signal from the brain and then is presented as a motor unit firing instance with different motor units firing at varying different rates. And the contraction of a single motor unit creates what we term as sort of the electrical signature of this sort of firing instance, and what we call commonly as a motor unit action potential, also otherwise known as a MUAP. And each of these motor unit action potential provides varying amplitudes of force seen below during that sort of twitch force, with the sort of quicker firing motor units, so the higher frequency ones, producing a slightly lower force output, and then the sort of less frequent and later recruited motor units representing a bigger twitch force at that point. And they're recruited in a relatively fixed order, whereby the first recruited are the sort of quicker firing motor units, and then progressively as you go along, you get the slower recruited, but the much larger sort of twitch force, which then contributes towards the movement. And the EMG signal that we do see on that sort of global scale is a composition and a superposition of all of those active motor units available in the area, which within the muscle, and it's sort of commonly used to provide valuable insight into human movement and neural control. So how difficult is it to measure EMG? And again, to quote Professor DeLuca, it's commonly seen as it's very easy to collect the data, but again, consequently, it is quite easy to abuse that data because it is a relatively complex signal that we do acquire. But the sort of difficulty in life is always just trying to make something very complicated seem very simple. And that is, again, what we try to do through education and by providing high precision technology to be able to decomplicate some of these nuances of the signal and then represent it in an easily digestible way for clinicians, practitioners, and rehabilitators. But there are sort of many factors that we really do have to take into consideration when interpreting and measuring the EMG signal. And from an intrinsic point of view, so these are factors that we can't always control, but it's really important to be aware of when interpreting the signal. So that is, rather than saying EMG is inherently limited, it's just making sure we are aware of these factors when we are interpreting and then doing any sort of analysis and recording of the EMG data to make sure that we're extrapolating any of the meaningful data that we do have and then applying it correctly to the research questions. But from the extrinsic point of view, these are the factors that we really can control through experimental design, through rigorous protocols, through skin preparation, but mainly through the use of really high quality data to be able to mitigate a lot of the sort of signal resolution, muscle crosstalk, line noise and movement artifact, which can introduce a lot of noise within the signal and can really dampen the actual electrical signal that's emanating from the muscle. And one of the cornerstones in the ability to capture the sort of the beauty of our neural network and the neural control system is to select and use high fidelity recording systems and technologies. And that's where Delsys really have made their name over the last 30, 35 years in the production of these high fidelity tools. And by choosing these sort of technologies, it allows you sort of full and flexible bandwidth settings and signals that allow you to synchronize across a variety of different sensors and use a smart electrode design to reduce or suppress sort of the introduction of unwanted noise and be able to offer you integration options into third-party devices to be able to sort of fuse a lot of these data networks to be able to inform more of a comprehensive view for human movement. And that's why I bring you on to the Trino wireless system. So it is a sort of really an ecosystem of tools that span sort of a different platform, from simple introductory tools with mobile units to more complex and sort of versatile tools with the research systems. And these integration possibilities allow you to collect in sort of the lab, in sort of home-based situations and clinical rehab centers, or outside in the real-world environments. And as I say, we've been around for a relatively long time now within the field of EMG. And 2008 was when we released our first wireless sensor with the sort of legacy button, which could normally be characterized by those sort of elevated arrow and the push button. But since then, sort of technology has moved on, the research has moved on, and as sort of the questions evolve, so must we in the technology that we provide. So it's why we continue to innovate in the world of technology, offering different tools and auxiliary tools such as the sort of the foot switch through the FSR to be able to give ground contact time for gait analysis, load cells to be able to infer force from sort of dynamometers, EKG to be able to then incorporate how the heart reacts to a lot of these muscular or sort of exercise parameters. And then as we sort of advance into some of these later years, 2017 was when we introduced our real sort of flagship sensor with the Trino Avanti sensor, which is now commonly used across applications within the human movement sciences field and provides really sort of unrivaled signal quality and high fidelity signals with robust data transmission. But then as we move forward, we have the Trino Galileo and NeuroMap software, which provides sort of a fascinating insight into the motor unit recruitment levels and firing patterns that we represented at the start of that sort of the finest element of neural control that we can estimate through, and again, through dynamic contractions. And this provides a sort of fascinating insight into how our brain controls movement. And then moving on to sort of, again, 2019 with the release of the Quattro sensor. So this is, again, a sort of smaller sensor head, but allows you sort of more specificity when looking to isolate muscles that are either small in profile or in a very sort of complex muscular architecture, such as the hands, the forearm, or even the face, where you may not have necessarily the space to be able to put multiple Avanti sensors, but you'd be able to use the smaller sensor head with the same sort of signal resolution to be able to output the signal from a variety of different muscles in a close area. And then 2021 released our first HD EMG sensor with the Trino Maze. And this is, again, a sort of step away from our sort of traditional bipolar signal, single channel sensors, where you can now get 16 channels of EMG sensor data from a single sensor head to offer really a spatial representation of how muscle activity may alter from varying different areas of the muscle in relation to how the muscle fiber architecture might change, or the recruitment levels, or how force then influences the spatial parameters of muscle recruitment. And in 2021, again, we also released our Trunio Lite system, which was a research grade tool, but enables you the flexibility to move outside of the lab. So with the sort of simple USB dongle, this can be plugged into a laptop or a Microsoft Surface Pro to give you the flexibility to go outside with your data collection and transmit data from up to 4 different sensors, and enables you a whole wide range of different possibilities for the data collection. And again, I think the graphic here really illustrates the need for high precision technology, because our bodily systems are so complex in their nature that we have sort of interweaving muscular architecture. As you see from just a simple movement with the bicep contracting to perform a sort of bicep curl, there are so many multiple muscles that are sort of in and around, and without that high precision, we can introduce a lot of noise from surrounding sort of biosignals from either neighboring muscles or from the cardiovascular system. And then even as you sort of spin round and look, you have multiple muscles that span across the deltoid. And when you look at the sort of rotator cuffs, how many muscles are in there, and the forearms. And this is when the high precision technology of sort of maybe like even the Quattro sensors, when you can use smaller sensor heads to be able to identify and accurately identify the muscular activity that emanates from each one of these specific and isolated muscles. So now it's sort of, again, really looking at the importance of combining EMG tools with sort of the kinematic outputs that we can get from sort of similar technologies to XSense with the IMU sensor fusion, to be able to give more of a holistic and sort of combined approach to human movement sciences. So this is, again, to build on kinematic analysis here. So as you can see, we bring up a similar graphic with the bicep curl being performed. And at this point, you'd be able to accurately determine sort of the angular sort of changes at the elbow joint through the joint kinematics, and then any sort of segmental velocities and angular rotations as well. But it doesn't really describe the whole picture from what you're seeing, because you have no real idea about what is driving that movement and how hard the muscle is working. Being able to sort of ask a athlete qualitatively, they could provide some level of feedback to say, is it hard or not? How much are they being physically exerted in that sort of exercise? But it doesn't offer you, as a clinician or a rehabilitator or a sports performance coach, a quantifiable metric to be able to say this is actively working the muscles which we're targeting. So when you're looking to build on that with the EMG signal, you can then output the same kinematic data, but you'll be able to see what level of muscular recruitment is being involved in that sort of exercise. So this, again, is a signal just from using a fairly light 5 kilogram weight. You can see the EMG signal is relatively low, because, as we say, from a muscular effort point of view, is one of the tools that EMG can be used to assess. It is a relatively easy task, because we're only moving a relatively small force through that sort of point of rotation at the elbow. But then as you increase the weight to, say, a 10 kilogram weight, this is when you see a much sort of higher muscle effort that's needs to be recruited by the athlete. Whereas if you're only looking at the kinematics, maybe at this point, there isn't a sort of clear discernible change in how those sort of kinematic parameters might change. But on a muscular level, the athlete is having to try much harder. And in the world of sort of sports performance, being able to assess this from an injury risk or from a sort of performance adaptation point of view, this is sort of really vital to be able to inform the sort of clinicians and rehabilitators' decisions. But even from an ergonomic point of view, where musculoskeletal disorders are quite widespread, and the effort is to sort of try and mitigate against this by reducing some of the kinematic factors and the occurrence of force through the muscles. Having insight into the level of muscular effort that does go into movement can provide critical insight to help better inform a lot of the practices that we do. So this really brings us on to the different ways in which we can analyze EMG data. And with this in mind, I've tried to present it in a relatively simple model for guiding the analysis. So you can see we've got three main categories. So sort of the physiological effect, the EMG signal characteristic, and then an example computation. And although I suspect we all understand that the analysis of any data is more involved than just a simplification that I have presented, there's a real sort of novelty in, again, sort of presenting and understanding complicated data in relatively simple ways to be able to be translated through to applied settings within sports performance. So firstly, we've focused again on the sort of muscular effort side, as sort of highlighted in that last example, by changing the relative load through a fixed joint angle. So where the user would desire to understand the physiological effect of how a muscle or multiple muscles are working, the EMG signal can be characterized and defined by its amplitude at that point. So the range in which the EMG signal sort of is represented over a fixed scale. And you can use a simple moving average window filter, such as a root mean square, or commonly referred to as an RMS, and then find that peak amplitude to then compare across, obviously with some form of normalization that always comes to be able to compare across muscles, across subjects, or even between intervention states. So as you obviously seen in the last example, as you increase the force or the torque around a joint, the EMG signal normally demonstrates an increase in signal amplitude. And this can be simply, again, demonstrated by a right-hand bicep curl with two different weights. And you can clearly see that the heavier weight does elicit a far larger EMG signal. And this area of exploration provides the user the ability to study the relative load across muscles between tasks and, again, across subject groups. So the next sort of physiological effect commonly studied in sort of EMG analysis would be the activation timing of muscles, also known as being sort of when the muscle is on or off. The user would be looking at the signal for when the amplitude goes above a sort of predetermined threshold. And this is when the muscle is really being determined as on and sort of contributing to the movement at that point. So a typical approach would be to filter the data with, again, a moving average window, and then use a threshold calculation based on the number of standard deviations above the baseline noise level to determine when the muscle is on or when it isn't off. And again, a quantification of the muscle on-off state is arguably the most common and therefore most sort of variance for analysis. This example uses sort of 3 deviations above the baseline noise level during repeated bouts of bicep curls. So you can see when the sort of red sort of arrow or red line goes above that standard deviation, that is when we are classifying the muscle as being actively contributing to the movement. And then the bottom graph shows how and when analyzing multiple muscles can help you to determine when muscles are contributing at the same time. So what we really refer to as co-contractions. And this, again, offers insights into the neuromuscular recruitment patterns and how this might alter over time, and if there's any sort of spasticity in the muscle, and what you might typically see from a healthy population against a non-healthy population. And then the final physiological effect that we do commonly analyze would be the muscle fatigue. And from an EMG signal, we can provide an estimate on fatigue through the inquiry of the frequency domain of the signal. And interestingly, the signal presents with an increase in EMG amplitude over time, but a decrease in the mean or median frequency analysis. So there are sort of, again, really many methods to study fatigue, where physiologists who would tend to monitor the failure point. We in biomechanics tend to be interested in the progression of fatigue and how we can extrapolate that from an EMG signal and a fatigue index. In this example, we have again used the bicep curl and the bicep brachii with a 10 kilogram fixed weight at a fixed joint position. And after 200 seconds, you can really see that sort of point failure has been reached, where the EMG amplitude has risen, but the frequency content has sort of decreased over time. And the bottom graph really shows that sort of frequency component, with the red line tending to demonstrate that the decrease in frequency has happened as the sort of contraction has progressed. Although, again, it is an attractive line of inquiry, we would encourage readers really to spend a little bit more time delving a little bit deeper into what this means and the different sort of options for EMG analysis and particularly fatigue analysis as well. And again, within the context of sports biomechanics, then EMG can be seen as a tool that really does provide quite easily accessible physiological data, which are responsible for generating force and producing movement. And it can help scientists in a variety of different ways, whether that's practitioners, athletes, or engineers looking to apply this in a wide variety of fields in sports biomechanics. And to give a little bit more of a sort of an applied setting about really why kinematics and EMG are needed to be able to fully assess a rehabilitation program, I wanted to demonstrate an applied example from the University of Wisconsin, who looked at the sort of return to play following an ACL sort of rupture and sort of post-surgery at that point. So to start any sort of rehab of the ACL, it really is important to consider the quadriceps, because quadriceps do play such a key dynamic stability role within dynamic function. But neuromuscular dysfunction of the quadriceps is extremely common following ACL reconstruction. And an inability to restore quadricep function and neuromuscular function can lead an athlete to a much higher risk of re-injury or asymmetries between the legs and biomechanical deficits, which would not only sort of negatively impact them in terms of injury risk, but also in terms of sports performance. So then we really need to ask the best way to be able to accurately assess an athlete's readiness to return to sport. One way to assess sort of the quadriceps strength is through an isometric or isokinetic dynamometer. And the data in red at the bottom is from the surgical limb or the injured limb. And the data from the top there with the black is from the non-injured limb. And just looking at the sort of basic sort of strength indices that we're seeing from the knee extensor torque, it is relatively good with interlimb symmetry around about 88%. And this is only sort of 5 months, 6 months post-surgery, which is, again, as a quantifiable metric of strength for the quadriceps is relatively good at that point as well. But when we move into a more dynamic situation, we're seeing much more sort of kinematic differences and deficiencies that are spanning sort of interlimb differences between that affected and non-affected side. So whilst running, we're seeing a sort of 14 degrees difference in the sort of maximal knee flexion, which is then translating into kinetic differences and performance dehancements or inhibitions at that point. So it's potentially better to be able to look at a sport-specific movement, because when breaking down running and looking at a lot of different sort of sporting movements, it's hard to be able to accurately assess an athlete's readiness to return to sport by looking at a sort of typical sort of ramp and hold exercise, because it's not how sort of normal maneuvers are really performed in that world. When you're looking at sort of sports that elicit high risks of ACL injuries, such as footballers, netballers, basketball, these sort of highly dynamic cutting maneuvers, where the sort of inverse relationship between the dynamic and sort of fast nature of the movement is inversely related to the time in which you have to produce the force to then control the knee function to make sure it doesn't slip into a disadvantaged position, which could introduce the re-injury rate. So it's really needed to be able to see what else is actually contributing to the asymmetries that we're seeing, if it's not just the maximal strength of the quadriceps at that point. So again, the same isometric test was done, but this time the participants were told to kick out as fast as they could. And what we saw was really big differences in terms of the rate of torque development, with the, again, rate of quadricep development, or the rate of force being much lower, with 41 to 60% asymmetries seen between the affected limb and the sort of injured limb. And within sporting maneuvers, what you really need is that sort of rapid rate of force development. If you're going into a cutting maneuver and you don't have the ability to rapidly activate and recruit the quadriceps, then it doesn't matter if you'll be able to sort of maximally produce the strength after half a second, because in that half a second, you've already gone into an injury producing sort of mechanism and kinematic position. And again, the same was seen during different functional testing. So really, no real good testing on a sort of isometric dynamometer in a very controlled environment, because sporting activities aren't in a controlled environment. So when we took this out into sort of jumping and running, we saw similar things in the sort of symmetry levels between the limbs, in that the affected limb was anywhere between sort of 60 and 80% of the non-injured limb. So at that point, rather than just looking at the strength, you really need to look at the neuromuscular function to be able to accurately determine whether an athlete might be ready to return to sport. And in terms of actually applying this in the real world, this is where sort of wireless technologies do really come into their own, where you can take these sort of experiments and interpretations outside of that typical lab environment and apply it into a real world functionality test to be able to accurately assess the readiness to return to sport. Okay, and again, just to move on to a couple of example applications that do apply both Delsys and XSense within the world of sports performance. So the first one that we have here is from INSEP. So this is the group with the sort of French athletics team sort of preparing for the upcoming Olympics, and they're looking at how 3D kinematics and EMG data can help to inform and help to better practice a lot of their sprinters in terms of Olympic readiness. And this is a sort of comparison of the 3D kinematics and EMG muscle activity between linear and curve sprinting during the acceleration phase. And what we have seen here is that there are differences between, especially in those sort of 200-meter sprints, where it's key to really understand the changes that we see between running that first bend during the acceleration phase and then transferring that power and velocity into the linear straight during the final 100 meters. And so why is this, I guess, important at that point? So 57% of the 200-meter race is running along the curve, along the bend. And it's been shown in sort of previous studies that speed decreases in comparison with linear sprinting because of greater left foot contact time, a reduction in the right step length, and kinematic modifications. And some of these kinematic modifications that occur on the bend and running the sort of curved response include sort of a greater left hip adduction, a greater touchdown distance, and a greater inward lean, which are all related and have been shown to contribute to a slower sprint performance, and could also be linked to sort of the force production alterations that we see during that initial phase of the sort of 200-meter sprint. And especially when you're looking at a reduction in sort of ground foot contact time, or sorry, it's sort of, again, eliciting sort of negative impacts for maximal force production and transferring that power through in sprinting. And the group INSEP have used the XSense and Delsys systems in combination, using the XSense sensors to be able to output those sort of kinematic variables in sort of in-field testing on the track, but then also using the Delsys EMG technology to look at 4 muscles bilaterally, so looking at the gastrocnemius medialis, the rectus femoris, the bicep femoris long head, and then also the vastus lateralis, to be able to see what sort of neuromuscular alterations may really contribute to the different and altered mechanics that happen on the curve sprinting, and if that is a sort of negative impact, and then maybe how they can train that towards being able to actively adapt training protocols or strength protocols to be able to increase sort of muscle output and kinematic output on that sort of curve sprinting side. So previous studies have sort of looked at some of the EMG changes in curve sprinting, and sort of differing responsibilities of legs do actively occur during sprinting, with the left leg, or sort of the inside leg at that point, is mainly responsible for stabilizing and managing the frontal plane by braking and changing the direction, with the right leg or the outside leg mainly responsible for propulsive forces and the support of motion in the horizontal plane. And again, previous research has shown that a higher peak EMG amplitude of the bicep femoris and glute medius in the inside leg while in the outside leg, higher activity was noted in the semitendinosus and the adductor muscles during the sort of curve sprinting. And other research, again, within the same area, has seen that EMG amplitudes, again, change dependent upon what lane they may have been in when sprinting, with the inside lane and a much sort of tighter radius, eliciting much higher EMG activity during that time. So if athletes on the outside, again, didn't have to alter the neuromuscular recruitment patterns quite as much to help stabilize and help sort of, again, keep the force propulsion through with any altered kinematics. And when potentially you hear people talking about sort of someone is a very good typical bend runner during sort of a 200-meter sprint, potentially this is because they've actively modified the way in which they recruit the either sort of muscles contributing to force propulsion and dynamic stability, and then how that translates into the kinematic effects. And the sort of novelty of the work in which INSEP are currently doing by combining these technologies allows for the sort of time synchronized data collection of both these kinematic and EMG parameters to show exactly how this is happening in the sort of real world environment, to see if there's any, again, link between the altered EMG and kinematic parameters. And from INSEP, we sort of, again, asked, so really what are the benefits of using XSense and DELSIS systems in this way? And the main things to come from it was a really sort of simple and easy setup for them in sort of in-field data collection, where the wireless sort of nature of both the systems allowed them to be uninhibited by sort of cables or sort of motion capture cameras, which you may have typically seen in lab setups. And again, not limited by a calibration range. So the main thing was the sort of, I guess, wireless transmission range. So at that point, they're able to measure the whole acceleration phase across the curve through the wireless technology. And this is something that would either be a long time to set up with motion capture, or sort of a very heavy calibration period to be able to accurately determine all of the sort of marker detection at that point. And this is all directly integrated into the XSense software for a simple utilization of both the systems, with easy use and export options to then further analyze the sort of parameters which they were seeing. And it's something that offers them sort of real world translatability to be able to inform sports performance and feedback to coaches about best practices to be able to inform training protocols. And then sort of one other one that may have come across recently was the 1 hour sort of cycling record. And this is, if anyone wasn't sort of familiar with the record, it is sort of one of the most physically grueling records that are around in elite sport, where over the course of an hour, a cyclist will go out by themselves and just try and cycle as far as physically possible within the hour. And we were lucky enough to be able to go down and use some of our EMG sensors during a training phase of this with a couple of the elite athletes who actually just recently broke a couple of records, with Joss Loudon breaking the female world record and Dan Bingham breaking the British world record. And to sort of demonstrate how EMG was really used in this environment, again, we can use it to study the effects of fatigue over the course of the hour to see how fatigue manifested through the again, elongation of the ride, and if that affected any asymmetries between the limbs, if that affected neuromuscular recruitment patterns, or if it led to suboptimal riding technique as well. So being able to combine a lot of those different metrics and analysis options that we did talk about earlier to see if what sort of level of fatigue they were looking at, the sort of muscular contraction and co-contraction, or muscle on-off timing if there was altered recruitment during that time, but then also the amplitudes, and then how each one of those sort of muscle producing or force producing muscles actively contributed towards the movement over that hour. And if there's any sort of training protocols that we could put in place, or bike optimization in terms of a higher seat or a change in cadence, a change in wattage to be able to output a higher force output for the rider, and then ultimately lead to an increase in sports performance. And just as a bit of feedback from the riders who we did do the biomechanical testing on, from Joss, sort of knowing that having the capabilities during that training run, she was able to go into the sort of real time trial and hour record attempts, knowing that her neuromuscular capacities would hold out at the required output that it would take and required wattage to break the hour record. And it, again, just really filled her with a lot of confidence to be able to actively go in there, knowing that she'd be able to sustain that power and that the fatigue would not reach such a critical limit where the output would then determine and lead to task failure. And with Dan, who is sort of an avid aerodynamicist, so always looks for different ways to which they can streamline performance to elicit sort of the marginal gains within sport. He said is sort of always using that EMG sensors to focus on the biomechanical factors that would increase the propulsive force and in effect increase the available power that was available to him during the entire duration. And that's exactly where the EMG sensors do come into their own. And just from sort of the example video here, you can see that the wireless nature of the EMG sensors enable us to collect data in sort of real world situations, and same for the XSense systems where you can't really reproduce this in a sort of stationary bike or get someone to cycle around a velodrome with motion capture systems with the cameras, because the calibration area again is just too high, and being able to feed back that sort of data from applied performance situations to coaches really helps enhance performance and enhance training protocols to get the small marginal gains that really make the difference at the elite level sport. And then in terms of some other sporting blogs, so we have a number of sort of application areas on our website with sort of short ideas and concepts about how EMG is currently used by a lot of our users. So you can read a lot more about the sort of 1 hour cycling record, about how the coaches tend to use the data, and then the feedback from Dan and Joss. But then also we have a really interesting application in motorsport about how we've been using our sensors live on track to be able to determine how riders can more efficiently and optimize their performance through a reduction in neuromuscular fatigue, through changes of technique with driving to see if they're using their right or left arm a little bit more sort of enhanced. And it also allows them sort of a novelty to be able to, again, squeeze that marginal gains from it. It's been used live on the track in F1, in motorsport, with motorbikes, with endurance racing, and also with rally driving as well. So it's the wireless technologies which really enable us to take a lot of these situations outside of those sort of typical lab environments. And finally, yeah, if there are any questions, I'd be happy to answer those. But please also feel free to connect with us across our sort of social media accounts, where we can be found at sort of the tag of Delsys Inc. But also feel free to connect with us on our website to see a little bit more about the product range, some of the application areas, and any sort of upcoming events and news that we do have as well. But again, also free to be contacted via email with any inquiries that you might have as well.
Thank you very much for this nice presentation. In my opinion, it was a really nice presentation, very clear. And luckily, we have also some good questions that came in. And I will start with the first one I have here. It is from Anand Bhushan, and he asks, how do you counter noise in EMG data?
Yeah, so again, this is why we really focus on such high fidelity and specific technology with the sort of onboard filtering to minimize sort of that movement artifact. And again, with appropriate sensor placement and skin preparation is a really big part of reducing any noise. So making sure that you remove any hair, any sort of loose skin or dead skin, and preparing with a small alcohol wipe, again, to remove any debris, and then making sure that you place the sensor on sort of the middle of the muscle belly at that point there, because if you're moving it towards sort of the muscular tendinous junction, what you'll be seeing is an introduction of noise at that point, also away from any innervation zones, but again, also away from sort of the muscle borders, so that you're not contaminating your EMG signal with muscle crosstalk from other areas. And sort of guidance on this can be found sort of on our website on a few of the technical notes, but also through the sort of CENIAM guidance, which is a sort of standard protocol, which is seen throughout the field. to make sure that you are appropriately positioning the EMG electrodes to elicit sort of nice, clean sort of baseline noise with high signal to noise resolution as well. But then sort of within the software that we also have, we also do provide sort of a live sort of signal quality monitoring tool, which enables you to make sure that sort of prior to any data collection, that you are seeing sort of a clean signal that accurately represents the muscular activity that's happening within that specific muscle.
Okay, thank you very much, Jonathan, for the answer. The next question is from Dr. Zartasha Mutansar. She has a few questions, basically. The first one is, how do we translate a signal into the amount of force we need to know?
Okay, yeah, so as sort of the example that we did show with looking at the signal amplitudes at that point, what we tend to do would be to, prior to any data collection, perform some sort of normalization trial, whether that is a sort of maximal voluntary contraction, where you typically perform some sort of constrained movement against a fixed force, and that elicits a maximal force production from the muscle. And after that, you can then normalize against that sort of 100% of maximal force production to then quantify how hard the muscle is sort of actively trying. And with that, when you perform this sort of normalization trial, you can then compare across sort of different muscles or different populations or different sort of intervention states, whether it is pre and post a fatiguing intervention, to see how fatigue then actively sort of introduces any sort of different neuromuscular recruitment patterns or inhibitions to produce maximal force output.
Okay, thank you, Jonathan. The second question she had was, for example, in regards to the last question, if I want to know the magnitude of a force due to deflection from a signal strength, how can you do that?
And again, yeah, in terms of actual force, EMG is a representation of the force, but along with the sort of intrinsic, extrinsic factors that we did see, it's not a direct fit. You can interpret the sort of force output, but implying this from the EMG amplitudes that we do see, again, is sort of the best avenue to be able to sort of infer the sort of force output of the muscle at that point. But again, making sure that you take into consideration some of these sort of extrinsic factors, particularly maybe sort of subcutaneous tissue at that point, as it is a sort of a filter on the electrical signal that then reaches the EMG surface electrodes at that point. But being able to normalize the data is really key, and there are lots of great papers that I'd be happy to share with anyone who wanted to reach out and have more in-depth discussion about the ways in which we can use EMG to imply sort of training adaptations or muscular adaptations, and how force then can be interpreted in those scenarios.
Okay, thank you, Jonathan. I have a next question. This one is from Sarah Tenberg. And at first, she thanks you for the very nice presentation. And she asks, I'm wondering for how long you can record EMG data and for how long you can record kinematic data with Xsens. Well,
yeah, I may leave the kinematic one to you.
Drift from inertial measurement units. So can you answer the question, please?
Yeah, I can answer it from an EMG side for sure. So with our sensors, they typically have a sort of 8-hour battery life. And this is sort of on a bit of a range on the sort of engineering side. So it is sort of 8 hours is your typical data collection time, or sort of maximal data collection time before that the batteries need to be recharged. So this really covers sort of the whole day span at that point. So it can be collected from sort of ecological data collection through sort of wireless data transmission and sort of mobile acquisition devices. And when combining with Xsens, you're able to then combine these tools to be able to output the EMG alongside the kinematic output there as well. And the sensors do recharge very, very quickly. So if it was completely dead, you'd be able to put the sensor back in the sort of charging cradle for sort of maybe 3 hours or so, or again, maybe charge it overnight. By the time you come back in the morning or the next day, the next sampling period, you'll be able to record again for another 8 hours or so. I don't know for battery time for the Xsens motion trackers.
Xsens, at Xsens we can measure for 6 hours at once. This in the meantime, it depends on the system you use, but for Awinda it's more than 6 hours. 6.5, and for the Link, it's around 10.5 hours. So.
Yeah. So yeah, the Avanti is a nice compromise between the two at that point.
Yeah. Okay, I have the next question, and I think this will be for now the last question, since we're almost out of time. For all the other questions, we save the questions and we'll come back to you in a later stage to answer all the questions. No thank you for sending these questions to us. The last question is from David Lopez Perez. And David, he works with infants in the first years of life. And his question is, do you think your sensors would be usable in such small populations to see how muscles are involved in acquisition of new skills, such as walking, reaching, crawling? If it is doable, how many sensors would be the minimum to get meaningful data from, for example, arms or legs?
Yeah, so again, our sensors have been used really widely within the pediatric populations. Again, it was the so when we're going through the sort of sensor lineup during the earlier phase of the presentation, what we have are sort of the smaller head sensors, which are sort of the Mini, the Duo, or the Quattro. So at that point, it's a much smaller surface area, because obviously we're dealing with pediatric populations with smaller muscle sizes. So the Avanti sensors are designed for sort of larger muscles, or it's harder to fit as many sensors on sort of smaller populations. So being able to get sort of 4 separate smaller muscle detection heads and use those on sort of the smaller area of the arms, of the legs, with these pediatric populations. And we've got many groups who do actively use this for, especially in young infants who go through such a fast range of sort of motor adaptations to be able to, and skill acquisition during those early stages. And we can use these with high fidelity to be able to accurately determine the sort of adaptations that we might be able to be seeing in sort of infants and sort of young children at that point as well. And from a number of sensors, I guess really it depends on how many muscle groups that you might be tending to look at from. With the system that we operate on, there's the capability to record up to 32 different EMG channels. But for a minimum, for sort of that sort of application for lower limb and potentially upper limb, you may be looking at somewhere around 10 channels. But for more sort of in-depth analysis, it'd be good to sort of speak further about the real areas of interest and which muscles might be specifically interesting for the application.